Hi, everyone. My name is Fatos Ismaili, and I'm a Chief AI Architect in the Microsoft's Customer Success Unit here in the UK.
Hi, everyone. I'm Tanuja Brahmdepati, Global Specialized AI Cloud Solution Architect at Microsoft Corp. Almost every team we work with says the same thing at some point after going live with their first agent. It worked perfectly in the demo. Why is it slow now? The honest answer is that the demo was never a predictor of production. Today is about why that gap exists and how to close it. Orchestration, speed, cost control. That's what we're going to cover in this session. Let me quickly place this in the bigger picture. Every agent program moves through the same 5 stages. Envision the use case and value. Build the agent's tools and data layer. Secure it with identity, safety, and compliance. Observe it with tracing, evals, and quality gates. And then, only then, optimize for speed, cost control, and scale. Most teams we meet are stuck in between stages 4 and 5. The thing works, users are on it, and it's slow, and the invoice is bigger than anyone's forecast. And if there's one mindset shift to walk in with, it's this. You never actually complete optimizing. You run it permanently the same way you never stop doing security. So, what does the gap look like? When we go into enterprise that's been running agents for a few months, we hear versions of the same 8 complaints, and each one maps to an architecture failure. Teams keep building agents nobody knows about. That's agent sprawl. Dozens of agents on different stacks, duplicated cost, inconsistent user experience. Our agents give contradictory answers. There's no shared memory. Every agent rediscovering the same data independently, and the inconsistencies compound. We keep rebuilding the same integrations. Tool duplication, the same connector re-implemented 3 or 4 times across teams, each copy with its own security drift. We have had an audit and couldn't explain what our agents did. Ungoverned identity, shared keys, overprivileged service principal, no audit trail. We can't debug it. Observability gaps, no central place of what ran or why. We can't switch models without rewriting everything. Model lock-in, hard-coded deployments with no failover. RAG quality varies widely across agents. Data plane chaos, vector stores, SQL, SharePoint, and graph wired ad hoc per agent. And we don't know the cost until the invoice lands, zero workload level attribution. Now, here's what ties all 8 together. Not one of these is a model problem. Swapping in this quarter's newest frontier model fixes none of them. They're architectural problems. And the answer is consistent architecture and agent mesh on Azure, which is what the rest of this session builds. Let's make architecture problem concrete. With the complaint we hear most, responses are slow. Now, slow doesn't sound like one problem, but it actually is about 4 different ones. And you have to figure out which one you've got before you spend any money fixing it. When a customer says that to me, my first question is, where does it feel slow? Is it wait before anything appears on the screen? That's time to first token. And it's driven by prompt size, queue depth, and network path to the deployment. Is it choppy once tokens start streaming? That's inter-token latency, a completely different root cause. Model decode, throughput, and capacity pressure. Is it total end-to-end time the problem? That points at the number of reasoning loops and tool calls in between. Or is it fine at 9 a.m. and slow at 2 p.m.? That's concurrency. You're hitting capacity limits under load, or your orchestration has no parallelism. That's 4 symptoms with 4 different fixes, and money spent on the wrong one is wasted. The equation on the slide is why agents break the old intuitions. Latency is loops multiplied by the sum of model inference, tool execution, and network overhead. And every loop re-incurs all 3 simultaneously. Double the loops and everything doubles. And that's why one user's single shot demo tells you nothing about production, with thousands of concurrent users and multi-turn sessions. And that's why the 8 problems from the last slide show up here. Sprawl means duplicate loops. No shared memory means repeated lookups. Data plane chaos means retrieval that overfetches on every request. The same diagnostic logic works at the agent system level too. How agents are designed and how they coordinate with each other. There are 4 failure patterns here, and you can usually spot them from symptom alone. What matters is that these are coordination and design mistakes, not model limitations. And they show up in nearly every failed deployment we see. The agent gets confused on complex questions and answers get worse as the conversation goes on. That's monolithic agent and one God agent carrying responsibilities that should be split up across the system, degrading under its own prompt complexity. Cost spikes overnight and nobody can explain it. Unbounded loop, no iteration limit, a failed operation retried all night, which adds significantly to the cost. Agent B contradicts what agent A just said. Context corruption chain, and this one is pure coordination failure. One agent writes bad state to shared memory, and every downstream agent inherits and amplifies it. And the sneakiest of all, it calls the right tool with nonsense parameters. Tool call ambiguity, vague descriptions, producing calls that are syntactically valid but logically wrong. No exception thrown. The code runs. The answer is just wrong, which is exactly why testing rarely catches it. So that's 8 anti-patterns at the platform level and 4 more in how agent systems are designed and coordinated. Fathos, where do you even start by fixing that many failure modes at once?
Okay, so everything we're going to dig into for the rest of this session comes back to one picture, this that you see right here, the 5-layer optimization model. If you take nothing else away today, take this structure because every lever we talk about lives on one of these 5 layers. Let's walk it up together. So layer 1 is about model selection. This is simply which model does each step of the job. And the trick here is right sizing to the task. Not everything needs your biggest, most expensive model. So you send the routine, low complexity work to a cheaper model or a lighter version of that model in the same family, and you save the heavy hitters or the heavier, more complex use cases for where they actually earn their keep. Layer 2 is about scale and context. Think of this as what actually goes into the model and what comes back out, the tokens in this case. How you compress them, how you cache them, how you structure your prompts and your conversation history. Get sloppy here and you're paying for the same context over and over. Layer 3 is about retrieval quality. This one's about what knowledge actually makes it to the model's context. And it's usually where the real problem hides. Your ingestion, your re-ranking, whether you're even measuring grounding precision, and so forth. If the right information isn't reaching the model, nothing downstream can save you. Layer 4 is about the all-important orchestration. Now we're talking about how your agents and tools work together. And my advice, start simple. Bound your loops so they can't run away from you and parallelize the work that's genuinely independent. Don't over-engineer this before you need to. And finally, layer 5 is infrastructure. This is how capacity gets provisioned and routed underneath it all. Multi-region deployment, hybrid capacity, gateway control, the plumbing that keeps the whole thing running at scale. Now, here's where it all comes together. Microsoft Foundry is the control plane that spans all 5 of these layers. So you've got model router for layer 1, APIM semantic cache and the agent optimizer for layer 2, Azure AI Surgeon Foundry IQ for layer 3, Foundry Agent Service and the Microsoft Agent Framework for layer 4, and PTUs or provisional throughput units plus distributed tracing for layer 5. One control plane, all 5 layers. And this is the bit I really want to land with you, which is optimizing one layer in isolation doesn't really fix your problem. It just moves the bottleneck somewhere else. You tune your model selection, and suddenly retrieval becomes a constraint. You fix retrieval, and orchestration starts to crack. So the discipline here is diagnose and work all 5 before you conclude that any single layer isn't enough. Treat them as a system, not as a checklist. All right, let's kick off at layer 1, model selection, because honestly, this is almost always your fastest win. Here is the habit I want you to watch for. Most teams wire everything up to a single frontier model and ship it. And it works. The demo's great, and then the bill lands. See, sending every request to your biggest model is the most expensive habit in production. And the sneaky part is, it's completely invisible until you hit scale. Picture a support bot answering, for example. The bot is answering the question, what time does the office open? And it's running that through your top-end reasoning model. It's fractions of a cent in a POC stage. But now times it up by a couple of 100,000 a day of those requests, and suddenly you're paying frontier prices for what's basically a lookup. Okay, 4 patterns exist out there to fix this, and the good news is they all stack up. Number 1, tiered or cascading. Try the small models first, and only escalate to the big ones when confidence is low. That one move usually results in 40 to 70% cost reduction, because let's be honest, most of your traffic is generally easy to process. Number 2, small model offload. Take your classification, extraction, formatting work, and push it onto open weight models like the Microsoft's Phi class family of models. This tends to be 2 to 5 times cheaper overall. Microsoft got multiple customers that have moved to low complexity tasks to models like Phi and other, let's say, simplistic models through the Azure AI Foundry platform, and that have reported considerable time and cost savings, while withholding quality and model output. And that's the bit I really want to land with you. Right-sizing your model is not a compromise. Number 3, model pooling by task family. Instead of one model doing it all, you run separate ones. Reasoning, summarization, extractions, embedding, each matched to the job. That's another 30 to 50% approximately in reduction in cost. And finally, number 4, the one everybody forgets, the non-LLM alternative. Here's the thing. If the task is deterministic in itself, don't call a model at all. Use code, rules, a lookup table. That doesn't just reduce your token cost, it wipes it out completely. Now, let's swiftly go to layer 2, which is about scale and context. Because once you've got the right model, the very next question is, what do you feed it with? Every token that goes into the model and comes back out, and how you compress it, and how you cache it, and how you structure it. All of these are important topics to talk about. And I want you to hold one picture in your head for this whole section, because everything here comes back to it. Look at the bloated agent turn. It loads every tool schema, the full conversation history, the top 20 retrieval chunks. And what does all of that add up to? Roughly around 60,000 tokens in this example. So 60,000 tokens to act on the 2,000 that actually matter. Just with that ratio for a second, 60,000 to use only 2. Now compare it to a lean turn. Same job, but this time it loads only the active skill, a summary instead of the full history, and just the top 3 chunks for the task in front of it. So only what this turn actually needs, pulled in on demand. And here's why this matters so much. Bloat context hurts you twice. First, you're paying for every single one of those wasted tokens. That's the obvious cost. But the second hit is the sneaky one. Your answer quality actually drops because the model loses the signal in all of that noise. So you're paying more to get a worse answer. So the goal for this entire layer is that simple. Make that lean bar your default, not the exception you reach for when costs blow up. Make it the default you start from. Okay, so one of the highest leverage ways to actually get to that lean bar, single scale, single responsibility design. Here's the core principle behind this. Each agent gets exactly one specialized skill and one clear domain of responsibility. That's it. And the reason that matters is twofold. First, it stops your prompts from fighting with each other. No more one agent trying to be 5 things at once. And second, it lets you parallelize cleanly, because when every agent owns its own lane, there's no coordination overhead to manage. Now, when you build those skills, build them as pure deterministic functions. Explicit inputs, explicit outputs, nothing hidden. Why? Because then you can test each one in isolation, and you can reuse it across agents instead of rewriting the same thing 5 times. And here's the mindset shift I really want you to take away. Flip your design order. Go tool first, not agent first. Most people start by asking, what agents do I need? And that's backwards. Start with the skills and tools your system actually needs, define those first, and then assign agents to orchestrate them. That one reordering is what genuinely stops duplicate skills quietly creeping in all over your system. And look, this isn't just a tidier architecture for its own sake. Systems built this way show 3 to 5 times faster task completion, and single skill agents typically cut prompts tokens count by 60 to 70%. So you're going faster and spending less. Cleaner design that happens to be cheaper to run, that is the win that you're getting from this. So quick one skill engineering, but an important one. There are 5 habits that separate skills that actually scale from skills that just sprawl into a mess. Let me run you through them. First up, scope narrowly. One workflow per skill, that's it. And here's why that matters. Small skills compose together beautifully, but mega skills, they bloat. So if you've got a skill that's trying to do 5 different things, be honest with yourself, that's not one skill, that's 5 wearing a trench coat. Next, name it for discovery. So name the skill for discovery. And this is one that people always overlook. Your names and your descriptions, that's literally how the agents decide which skill to reach out for. So treat them like you're designing an API, not writing documentation nobody reads, because a vague, fuzzy name is just a skill that never gets picked. It might as well not exist. Third, prefer scripts to prose. Look, if the steps are deterministic, if it's the same every time, write it as code, not as instructions. Save your reasoning tokens for the calls that actually need judgment. Don't burn them asking the model to refigure out something a simple script or Python code could just do. Instantly, every time. Fourth, reuse and chain. Compose your skills into bigger automations. Please don't copy-paste the same instructions across 10 different agents. Write it once and chain it wherever you need it. Your future selves will thank you. And last, version and evaluate. Treat your skills like software, because that's what they are. Versioned, tested against evals, rolled out gradually, not something you quietly tweak in production on a Friday afternoon and cross your fingers. So the whole thing boils down to this. Small, well-named, tested, reusable skills. Engineer your skills like code, because genuinely, that's exactly what they are. So we've just tightened up the architecture. One skill per agent, clean lanes, pure functions. But here's the thing. You can have the leanest agent design in the world and still bleed tokens if the prompt itself is a mess. So let's bring that same discipline down one more level to the prompt itself. And here's the kicker for this. The single cheapest optimization available to you, full stop, is just structuring your prompt correctly. No new model, no new infrastructure, just putting things in the right order. And here's the mental model I want you to carry with this. Every prompt has 2 zones, a static zone and a dynamic zone. And there's a line between them called the KV cache, prefix boundary. Now, everything above that line, your system instructions, your persona, your tool definitions, your few shot examples, that stuff is stable. It doesn't change turn to turn. So it goes at the top. And here's why that matters. Everything above the boundary is eligible for cache reuse. You're not paying to reprocess it every single time. Everything below the line, the user's message, the retrieved chunks, the turn history, that changes every turn. So it goes at the bottom where it belongs. Now let me call out the anti-patterns because these are the ones that I see everywhere. Dumping in your full conversation history with no summarization, injecting 10 plus static few shot examples on every single turn. Verbose tool schemas, loaded regardless of whether they're even relevant. And my favorite, duplicating the same instructions in both the system prompt and the user message. Every one of these quietly wrecks your cache hit rate. So stack the fixes together, prompt and skill compression, context window pruning, dynamic few shot selection, tool description minimization. And here's the headline of all of this. Disciplined context management alone cuts your token cost by 40 to 60%. And that's before you've touched a single piece of the infrastructure. So that's the layers 1 and 2, the right model fed in the right amount. Tanuja, let me hand to you now. So what's the one design decision you see most teams get backwards before they've even written a prompt?
It's this. Teams reach for the wrong mechanism for the job, and there are only 4 to choose between. The easiest way to see it is with one running example, a customer support agent. Let's start with top left, the step-by-step process for handling a return. Check eligibility, generate the label, log it. That's a skill, a reusable playbook loaded on demand instead of re-explained in every prompt. And it's the most underused of the 4. Looking up an order status, That's a tool, a direct API call, no reasoning needed or wanted. And keep the schema tight because it costs tokens every turn. Explaining this week's return policy, that's right. Fresh, factual, citable context that changes faster than you could retrain. So ground the answer in whatever the policy doc says today. And always responding in the brand tone, that's fine tuning territory. Stable behavioral priors, but only worth it at serious volumes. The key here is most teams cram everything into system prompt or into RAG, exactly the things that should be skills, and that's where the token waste hides. Match mechanism to job, and a lot of costs disappears. Orchestration. Layer 3, the principle in one line. Adding more agents is a cost upgrade before it's a capability upgrade. So choose the smallest topology that reliably meets the requirements. Staying with the support agent example, first step of the ladder, single agent, bounded toolset. FAQs, order lookups, done. Minimum overhead, the starting point for every new design. Next step, same agent, but the return process runs as a deterministic workflow. Checks eligibility, generate label, log it as code, not as model calls, because deterministic code is nearly free and model calls are not. Third step, support grows to cover billing disputes and technical troubleshooting. One agent genuinely can't hold it. So planet agent routes to specialist subagents. Legitimate, but every handoff adds context transfer, round trip latency. So you climb here only when you must. Last step, peer multi-agent mesh. Agents negotiating as equals with no planner. Highest coordination and token overhead. Some workloads truly need it, but to be honest, most that use it don't. On the tool call side, 4 patterns that matter daily. Parallel execution of independent calls, result summarization instead of raw dumps back into context, minimal tool descriptions, and tool caching in Redis. And the anti patterns to actively prevent repeating expensive subtasks across agent calls, blocking the parent on long running sub agent work, one agent consuming the entire session's token budget, and looping after the answer is already sufficient. There's one piece worth noting at this layer. The agent optimizer in Foundry Agent Service announced at Build and rolling out in public preview right now, it automates an improvement cycle most teams still do by hand. Picture this. Our support agent is live and it keeps making 2 mistakes. It looks up orders without confirming the order number first, and it answers warranty questions without checking the purchase date. Today, fixing that means someone rewrites the system prompt by hand, ships it, and hopes nothing else broke. The optimizer replaces this with a closed loop. It evaluates the baseline. The agent runs a task set, each task scored against explicit pass fail criteria, producing a composite score of, for example, 0 to 1. So those 2 failures become a number, not a feeling. It generates candidates targeted at what fail, rewritten instructions, a new skill for the warranty check, sometimes a different model for the quality cost trade-off, or sharpened tool descriptions. Then it runs every candidate through the same task. The baseline just fails. So you can see exactly which fix actually moved the score and what each one costs in tokens. And when you pick the winner, one command ships it as a new version of the agent. So it's fully auditable and you can roll back just as easily. In a run like this, the score went from 0.6 to 0.92 in minutes. No retraining, no code changes. And it starts with one command, AZD AI agent optimize. The optimizer is the safety net, though, for agents already in production. Good tool design means there's less for it to clean up, and tool schemas fail the same few ways everywhere. Vague descriptions. The model can't tell from get customer data whether that serves a name lookup or an account balance, so it guesses. The fix costs nothing. One clear sentence per tool, one per parameter. Signal, not prose. Loose types. Free text where an enum should be numbers with no min max and the model hallucinates valid looking wrong values. Oversized tool sets. A 30 tool schema loaded every turn when the steps needs 5 pays for 30 descriptions before a single call happens. So prune per turn. Ambiguous names. Get data, process request. Use verb underscore noun. Get customer. Create ticket. And the model picks the right tool from the name before it reads the description. On the reliability side, 3 things you want in place from day one. Every mutating tool idempotent with idempotencies key, so a retry doesn't create a duplicate refund. Explicit timeouts with structured errors, so the agent retries or escalates instead of hanging, and compact summaries return to the context window, and never a raw API dump. And the question I constantly get is, when do I actually split into multiple agents? The honest answer, later than you think. Most teams split for their diagram, not the workload. 3 questions settle it. Is the work genuinely parallelizable, or does step 2 always wait for step 1? Sequential steps that share context belong in one agent with skills. Could a well-designed skill do what a sub-agent does? If yes, the sub-agent exists for tidiness, and tidiness isn't worth the coordination overhead. Is the latency budget tight? Every split adds a handoff. Every handoff adds round-trip time. Split when the reasons are real. Different steps need different models or different permissions. Isolation genuinely matters for blast radius, tenancy, or compliance, or the handouts become chatty, long state transfers moving back and forth every turn, which is the architecture telling you it's fighting the work. That covers how agents coordinate. So, Fatos, tell me how we can stop these systems failing expensively at 3 a.m. in the morning.
Honestly, one word, bounds. You bound every single agent run because here's the principle I want you to remember. Bounded agents fail cheap and they fail predictably. Unbounded agents, they're the ones that fail expensively at 3 a.m. while you're asleep and the meter's running. So let me give you the 4 guardrails that make that happen. First, token and cost budgets. You enforce these in the orchestrator, per run and per tenant. So no single run and no single customer can blow the whole thing up. And the key detail, you want graceful degradation, not a hard stop. When it hits the ceiling, it eases off. It doesn't just slam the door on the user. Second, timeouts and fallbacks on every model and tool call. Timebox everything. And when something's slow or unresponsive, you fall back to a smaller model or a cached answer, rather than just hanging there. A hung agent is a terrible experience, and it's a completely avoidable one. Third, tracing built in on every hub through Agent Framework and Foundry tracing. And this one is simple. You cannot optimize what you cannot see. If you don't have visibility into every step of the run, you're flying blind. You've got no idea whether the cost is on latency or is actually coming from something else. And fourth, turn and depth limits. Hard caps on your loop iterations and your recursion. Because a one-way loop on agent stuck calling itself over and over, that is the agentic equivalent of an outage. It's 3 a.m. failure right there. So the overall message here is bound the budget, bound the time, see every hub, and cap the loops. 4 guardrails, and your system fails cheap instead of catastrophic. Now layer 4, retrieval quality. And this is where the biggest grounding wins live. So we've bounded how the agent runs. But here's the thing, a perfectly bounded agent that's fed the wrong information will still hand you a confidently wrong answer. Guardrails control the behavior. They do nothing for what the agent actually knows. So let's move from how it runs to what it's working with, retrieval. And if retrieval quality is the biggest lever on answer quality, and it is, then this is where you pull it. Fixing chunking, embeddings, and re-ranking typically lifts grounding precision from 30 to 50% before you touch the model. It's a 5-stage pipeline. Let's break that down. Stage 1, chunking. For enterprise documents, 512 to 1024 tokens is a sweet spot, with 10 to 15% overlap to preserve context across boundaries. And chunk semantically, not in arbitrary fixed sizes. Then enrich every chunk with title, section, date, and author metadata, or any other metadata that you deem it relevant for your specific domain. Stage 2, the embedding models, 1,536 dimensions for large corpora, 768 for a focused domain. And if you fine-tune your embeddings, that buys you another 15 to 20% precision increase. Stage 3, which is all about hybrid search, BM25 for keywords and proper nouns, vector search for semantic similarity. When fused together with reciprocal rank fusion, that gives you hybrid search. And Azure AI Search does hybrid plus semantic ranking all in a single call. Stage 4, which is about semantic re-ranking. A cross-encoder rescores your candidates, takes your top 20 to 50 results, returns the top 5 to 10, and again, the AI Search semantic ranker does this with no extra inferencing call. Stage 5, metadata filtering. Pre-filter by date, by type, department, or security label before similarity search even runs in the engine. So you're only searching what's relevant. And here's the payoff, because the numbers move a lot. Context precision goes from roughly 45% to 75%. Answer groundedness goes from 55 to 85%. And average tokens per query drops from around 3,200 to down to 1,800, a 44% cut. Hybrid retrieval alone has 15 to 25% recall over a vector-only baseline. So better answers, better grounded on fewer tokens. That's the rare optimization that improves quality and cuts costs at the same time. And none of those numbers mean anything if you're not measuring them. Close the loop with retrieval evals, measure groundedness, relevance, and citation accuracy. Diagnose whether the problem is the chunking, the search, or the k-value. Tune one stage at a time, and ship with evals running as regression gates in a CI/CD process. If you cannot measure retrieval quality, every tuning change you make is a guess. Instrument first, tune second. And if you would like to learn more about this, visit aks.ms/governedwithAgentOps, which will give you more information on this topic. Great, so now we've got the model right and the context lean, but none of that matters if the plumbing underneath is slow or over-provisioned. So let's talk layer 5, which is all about infrastructure and FinOps. I want to start with the part your users feel most, even though they've never seen it, latency. Because latency isn't a model problem, it's an infrastructure problem. It's decided by where your computer sits and the path a request takes. Here's a number that makes it urgent. Users disengage after just 400 to 800 milliseconds of silence. So time to first token is a trust problem before it's a performance one. And the biggest culprit is network geometry. Teams tune their prompts to death, then let the request bounce across 3 regions to get answered. Nobody's looking at it. So 2 kinds of latency exist from 2 different parts of your infrastructure. Time to first token, which is about the pause before anything appears, comes from the prompt size, the queue depth, the network path. You fix it by shrinking the context, by co-locating services, and streaming immediately. The other one is intertoken latency. The flow once output starts comes from decoding throughput and capacity pressure. You fix that with smaller modules per step and proper capacity sizing. So getting the infrastructure right and a good loop turn looks like this. Hydrate state from Cosmos DB, route through a fast model, fetch tools concurrently, stream tokens early. Topology and capacity choices, not prompt tweaks. It lands on 3 patterns. Stream always, linear semantic cache, the fastest call is the one you never make, and use smaller models wherever they're good enough. Great, so we talked about latency, and let's see how we can tackle this from a scale perspective. The number 1 barrier to horizontal scale is stateful in-memory agents. The fix is to externalize state, design explicitly for failure modes, and govern the whole fleet through one control plane. Let's focus bit by bit on this slide. So the first thing to think about is the reliability. So don't keep state in the server. Append has the request to the compute pulls state from Cosmos DB, does the work, writes it back, and lets the thread go. Nothing lives in RAM, so you can spin compute up and down freely. Balancing traffic across regions. So with this, we mean round robin when loads are even. Priority based when you want PTUs first and pay-go as backup, or a 70-30 split for active-active, and a circuit breaker that trips the moment you hit a 4 to 9 error. So these are ways we can balance the traffic across regions. When things go wrong, for example, we hit a rate limit, fail over to another region, or spill from PTUs to PayGo. When a tool is down, serve a stale cache and tell the user if that happens. Agent stuck in a loop counter caps it and returns it an error card so that the user is aware about it. If the agent restarts suddenly, it picks up back from the Cosmos DB state. These are some of the ways that you can mitigate around these failure modes. When it comes to governance, there's 4 things to lock down. First, control. Foundry control plane, Agent 365, Azure policy. Next is identity. You can do that with intra-agent ID and RBAC controls where no shared keys are present, no overprivileged service principles exist. On the safety side, you can leverage Foundry guardrails, continuous evaluations, red teaming, and evaluation gates before anything ships into production. And last, detection. Defender for AI, Azure Monitor, Sentinel, Purview gives you that control plane for detection if anything goes wrong. From a geography perspective, because someone always asks, can't we just deploy global for the best price? As you know, we have various different deployment options within Azure, global, data zone, regional. But sometimes the best decision order is fixed, and it's not the order people expect. So sometimes we have to think about the residency first, then latency, then cost. So if the data can't leave, for example, the European region or a specific country, that constraints the size before price gets a vote in the decisioning. So 3 deployment options along the spectrum, as I mentioned. 1 is global deployment option, which offers the best price and capacity. Traffic in that deployment option is processed anywhere. So the default for residency flexible, latency tolerant workloads is usually global. Data zone deployment options. The processing is constrained to a geographic zone, for example, like the European boundary or the US boundary. The residency versus capacity middle ground. That's what data zone gives you. And then finally, the regional deployment option, which is usually pinned to one specific region, which offers the strictest residency and the lowest network latency at capacity premium. In practice, most enterprises run a mix of these deployment options, global for general inferencing, regional or data zone for anything touching regulated data. So let me tell you about an organization because you've either lived this one or you're about to live it. Nobody sets out to build a mess, or one team spins up something with AI, it works, it's brilliant, so another one does it, then another one, and pretty soon you've got 22 product departments all building AI and all building it differently. It just grew suddenly. Everyone is thrilled until the question starts. Finance asks what it's costing, nobody can answer because there's no shared telemetry to even see the spend. Security asks if they're compliant, a shrug, because every team made its own choices. Then someone tries to scale it, and it falls over 10 concurrent users. 10. That's the most the penny drops. This isn't a product problem, it's an architectural problem. So here's what they did, and it's one decision. Route 100% of AI calls through a single AI gateway, one front door for everything. And watch what that unlocks. Real-time telemetry and chargeback down at the token level. You can finally see and bill exactly who's spending what. Semantic caching doing double the duty, cost and performance. Standardized security assures latency, and quality policy is across all 22 departments, and load balance through the gateway. They went from 10 users to thousands of users, all by adopting this AI gateway. So same teams, but the difference here is one architectural decision which resolved an issue with a fragmented sprawl of agents becoming governed, observable, and enterprise grade. And observable is the world I'll sit down here because once every token flows through one place and you can see the spend, the real question is, how do you manage it? So how do you put budgets, forecasting, and accountability around agents that decides their own workload at runtime? So Tanuja, what does FinOps look like when it's built for agentic AI?
Here's how the conversation usually starts. Someone opens the monthly Azure invoice, sees the AI number, and can't answer a single follow-up. Which teams own it? Why did it jump 40%? That's the FinOps problem, and the agents make it worse than normal cloud spend because reasoning costs aren't linear. A small share of sessions, the long multi-turn ones with heavy tool use and big contexts, drives a disproportionate share of the bill. There are 2 things I want you to take from this slide. First, everything we've shown today compounds 20% from routing, 30% from context compression, times 40 from retrieval, multiplies well past any single lever. And the second, on the operational side, tag every resource by workload, team, and environment before anything else, because attribution after the fact is nearly impossible. Pull APIM token metrics. When I say APIM, I mean API management token metrics per application with budgets and alerts before month end. Set rate limits with circuit breakers on HTTP 429 so a runaway session hits a wall before it hits the invoice. And report to stakeholders in cost per resolved task, not raw token counts, because that's something the unit leadership can't act on. Worth knowing, Foundry now has a return on investment for agents in Powered Preview, which computes exactly that cost against task completion and time saved. The other line I constantly hear is we did a cost optimization sprint last quarter and the savings already eroded. Of course they did. This is a cycle, not a sprint, and most teams run one stage of four. Visibility. See every token per agent and per tenant, or everything downstream is guesswork. Then you allocate it. Which team, which feature, which customer is that spend attached to? That's the step that changes what you can say in the room. Instead of AI cost went up, you can say the warranty check agent on the retail team drove 60% of last month's overage. And now someone can do something about it. Then you optimize using everything we've covered today, but aimed at whatever allocation just pointed to, and not everything at once. And then you forecast, so committing capacity ahead of demand instead of reacting after it arrives. And one organizational truth to close on: engineering owns the levers, finance owns the targets, and the cycle only works when both are looking at the same numbers in the same dashboard. One quick practical note: because you're managing a multi model estate now and it builds on two rails. Microsoft models sell directly GPT, MAI, Grok, DeepSeek, Llama build natively through Azure. Partner models like Claude build through the Azure Marketplace. And worth knowing, Claude just went generally available in Foundry, hosted on Azure, build as one consolidated line and counting toward your Azure commitment. The reason I flag any of this is because we've watched teams pick a model based on the billing rail they were comfortable with rather than the model that fit the task. We don't recommend that. Instead, Foundry plus Azure Cost Management gives you one cost and governance view across both rails. Same tags, same budgets, same dashboard. Billing is an accounting detail. It should never drive a model choice. How do I even forecast AI spend? It's not like a VM with an hourly rate. And the answer is to flip that question: forecast demand, not spend. Model how many tokens each feature consumes per team cohort. And the spend number falls out of your routing mix. Commitments: move proven steady state load to PTU reservations, keep experimental load on PayGo, and the classic mix is committing reserve capacity to a workload that hasn't stabilized. Guardrails per tenant rate and budget caps that degrade gracefully. A smaller model or shorter context before a hard cutoff, because a slightly leaner answer beats an error or a rate limit. And the habit separating surprise teams from calm ones, reforecast on every release. A single prompt change can move token cost 30% overnight in either direction. The forecast is a living document with a 5-minute review per release, not a quarterly artifact. So, Fathos, with agents deciding their own workload at runtime, how do we actually keep the cost under control in a systematic way?
That's the right question, Tanuja, and it's the one traditional FinOps cannot answer because the agents decide their own workload on the fly. You're no longer budgeting a fixed number of calls, you're budgeting a system that chooses how hard to work. So here's how you rebuild FinOps for that reality. 5 patterns, all living in the AI gateway. Cost attribution: every call tagged with workload and team ID. So spend is traceable down to the individual agent. You cannot manage what you cannot attribute. Token budgets. Per app quotas set in policy with a circuit breaker at 90% of monthly spend. It stops the overage before it happens, not in the post-mortem. Third, multi-tier routing. PTU capacity first, pay-as-you-go as backup, batch API for asynchronous work, every request in its cheapest viable home, and no code changes to go there. And then lastly, semantic caching, typically a 20 to 30% hit rate, and every hit is a model call you simply never pay for. Stack those four, and you got the picture on the right. Same 60,000 a month starting point. Without controls, it doubles to 120 grand in 6 months and keeps climbing. With a gateway in place, it comes down to around 42. Same workload. Now, the mindset I want you to leave with is this. Optimization isn't a project with an end date. It's continuous. Review cost, latency, and quality every month, and never ship a major change to 100% of traffic without a gated A/B testing. Here's that discipline in practice. Upgrading a model? Don't swap and pray. Route 90% to your baseline, 10% to the candidate model, and compare quality, latency, cost, and failure rate through APIM weight routing across at least one full business cycle, because month end doesn't look like a Tuesday, and the rollout is gated. So awareness, evaluation, shadow 5% for 48 hours, then increase that percentage to 10, to 25, to 50, and only then to 100, or you retire the application that leverages that if it's not behaving the right way. So a bad change gets caught at 5%, not at 100%. Then the checklist itself splits clearly across three main goals, which are to reduce the cost. So right-size models, compress and prune context, cache prompts and deterministic results, move batch work off the real-time path, and attribute spend by workload. Second, to reduce latency, stream responses, co-locate compute and state, parallelize independent tool calls, warm critical replicas ahead of spikes, and protect quota at the gateway. And third, to improve quality, fix chunking and re-ranking, back every prompt change with an evaluation run, filter retrieval with metadata before re-ranking, bound loops and delegation depth, and trace feedback back to the specific turn. Same three levers we've talked about all session, which is cost, latency, and quality. This is just running the checklist that keeps them honest month after month. And last one, governance. And here's a single idea to anchor on. Every agent is a non-human identity, and it deserves exactly the same rigor you would give a human service principle. Least privilege, managed identity, and audit trails. In production, those aren't nice to haves, they're non-negotiable. 4 pillars I want you to think about when it comes to this. Govern and control. So that's the first one. Register every agent in the Foundry control plane with its own identity and resource budget. Enforce allowed regions and residency through Azure policy. Catalog every live agent in Agent 365, owner, last active timestamp, and gate every production deployment behind on evaluation score threshold. No agent ships unproven. Second of the controls is identity and access. Use Entra Agent ID as a managed identity. Never service principal passwords, never shared API keys. RBAC controls at the resource level, read only by default. Minimum token scope per tool call, and automatic credential rotation with a monthly audit of last use timestamps. Third control, which is around protection and detection. Azure AI Content Safety, blocking prompt injection, jailbreaks, and PII exfiltration in real time. Defender for AI allows you to perform threat detection across inputs and outputs wired into Sentinel. Input validation stripping, control characters and rejecting known injection patterns, and output filtering, scanning every response before it reaches the user. And fourth control, audit and compliance. So Purview tracking provides data lineage and sensitivity labels through every tool call. Every action logged to Azure Monitor by trace ID, agent ID, tool name, and input hash. A 90-day hot log with an archive tier, and a quarterly red team exercise against your production endpoints. And keep the top threat vectors front of mind. Overprivileged tool scopes, session tokens leaked through verbose logging, supply chain risk from third-party connectors, and prompt injection through user input or retrieved documents. Bottom line is, treat your agents like the privileged identities that they are, and govern them like it. So from day one, not after the incident. That's trust and scale covered. Now, Tanuja, last question of the day. How do we actually know any of this is working once it's live?
Well, the honest answer is you don't know unless you set up tracing and monitoring from the start. Without that, you're guessing. And what makes guessing dangerous is here's the symptoms on the surface point you at the wrong causes. Let me close the loop on where we started. A customer says our agent is slow. At the start of the session, that was a dead end sentence. With distributed tracing, it's a 5-minute investigation because every run produces a connected trace chain, agent span with session ID, turn number, and the token counts. A model span with deployment, prompt, and completion tokens, and the time to first token. So if the time to first token is high, you're looking at the prompt size, queue depth, or network path. Tool call spans with execution latency and cache hit or miss, which shows you the sequential calls that could run in parallel. And RAG span, retrieval augmented generation span, with retrieval latency and grounding score. And if the grounding is low, latency was never really your problem. Quality was. And fixing the speed without fixing retrieval gets you fast wrong answers. Every span carries a correlation across every hop. So you reconstruct any session in sequence. That's what turns it slow into the warranty check tool adds 1.2 seconds because it runs sequentially after the order lookup when it could run in parallel. That's a one-line fix found in minutes. Foundry tracing and evaluation now extends to any framework in public preview, LangChain, the OpenAI SDK, Microsoft Agent Framework, or custom code, all through one open telemetry pipeline into a single trace view. So we built on something else is no longer a reason to not have the right insights. And the 3 alert domains every deployment needs from day one: cost at 80% of monthly budget with circuit breaker at 100. Latency, when P95 time to first token exceeds 800 milliseconds. And the quality, when eval pass rate drops more than 5% week over week. The last one is the one most teams skip. And that's the one that catches model drift and retrieval augmented generation degradation before users file it as a complaint. Where do we actually start is the question after every session like this. And the answer is a 4-phase sequence where order matters more than content. Phase 1, audit, not optimize. Map every agent workflow, prompt, and retrieval path. Identify the high cost and slowest user journeys, and record baselines in application insights. Because optimizing before baselining means never knowing whether anything helped. Phase 2, lock it down and switch the monitoring on. APM management, routing, shields, and content safety. State out of memory into Cosmo DB, cost attribution tags, and budget alerts on. Controls before changes, always, because an ungoverned system is not a safe place to make changes at scale. Phase 3, optimize. Now with baselines and guardrails, semantic caching on, PTU where the break even justifies it, context pruning, model routing, and retrieval fixes aimed at the journeys phase 1 surfaced. Phase 4, make it routine. Dashboards, operating playbooks, the A/B discipline we covered, and a standing monthly review. The 6 principles on the slide are the culture that outlives the roadmap. And if you keep one, measure it before you change anything. Which brings us to the one key takeaway from this session. Not a technique, not a number. The optimization is a loop, not a project. Teams that treat it as a sprint have this conversation again in 6 months when the next model ships or traffic doubles. Teams that build the loop, observe, evaluate, fix the biggest thing, repeat, compound their gains instant. And here's the thought to leave on. Model prices and capabilities are shifting every quarter right now. Without the loop, that's a recurring disruption. With it, every release is a free option. Rerun your routing policy, capture another 20 or 30%, move on. Same market, but a completely different experience of it. Thank you for joining this session today, and we look forward to partnering with you on your path to production journey.